Alright, hell yeah. So this video might be 3 parts. So there was a commenter that wanted to know about spheres, you know what I mean? And so we got spherical wheels on that vehicle. And then we have a bowling ball used as a pulley. And then we have a sphere rolling down a hill. So this might be 3 parts, or let's see if we can just get it all done in one. Now I do encourage people to, send me links or problem descriptions of problems that you want me to do instead of general vague ideas. But if you got something general and vague, hell yeah, I can do 5 minutes kind of on all 3 of these topics. And we'll see, maybe I do 3 hours, you never know. But anyway, so the question I pose for these 3 vehicles, I'm going to set it up where they're kind of at the top of a hill. They got some speed, and then all 3 of them threw on the brakes. So this one still makes sense. You got this red car coming in fast. It has square wheels. They threw on the brakes, so now we just have square wheels sliding across an icy surface. Pretend this is icy, not snowy. And so they're just going to be picking up speed. There is no friction, let's say, until you get to this dry patch of road. And then it's going to be hella friction. And then so the question is, which car will slow first? And all 3 cars are going to be the same weight. And this is one of those trick questions that I hate. You know what I mean? I don't like this when you're just like, well, I don't know, and it's probably a trick. But I guess the answer is they'll all stop at the same time. Because the force of friction that's going to slow these cars down is going to be the same no matter if you have this big old wide, flat and wide tire, or these tires that are wide, but then the contact point is just right underneath, or this spherical tire, where your contact point is just very small, I guess. But, I mean, from a theoretical perspective, is since these are soft tires, that the contact patch will be the same with these as they will with these. But just say, let's say the PSI is so taut in here that they're not only spherical tires, but they're not air pressurized. They're actually solid spheres of metal, and then you have rubber on the outside. So there's no there's very little compressibility. So these will just be, like 1 inch, let's say 1 inch of contact surface, where hell yeah, these are going to be like 8 inches wide, and then maybe 3 inches, 8 by 3 inches, where this is just literally a 1 by 1 contact surface. Now this is just going to be hella, whatever that would be. It's huge, 8 by 2 feet, so 8 by 24. But the idea is that it doesn't matter what the contact patch is. The force of friction, so let's do some writing. So you have the force of friction is this coefficient, and in this case of kinetic friction, let's say it's just 1. So then that just means it's 1. Who cares? And then it could be 0.5. It can't be more than 1, I don't think. But anyway, and then it's just times the normal force. The normal force is just the weight of the car. So the force of friction that's slowing these cars down is just equal to, in this case, if the coefficient is 1, it's just equal to their weight. So in all 3 cases, that force of friction is just going to be equal to their weight. All 3 cars weigh the same, so all 3 have the same slowing force on them. And I just think that's fascinating, you know what I mean? And so I guess we, now we'll kind of dive into at least one concept of maybe why this is the case. And especially, and it does apply to this sphere acting as a pulley, because what I want to do is like kind of follow the motion, kind of from the Newtonian perspective, is if we have like a chunk of mass, let's say it could be on a frictionless hockey rink or something like ice, or it could just be the only chunk of mass in the known universe. But on both of these, we could apply a force to it, and let's say this chunk of mass has 0 velocity. And when we do apply a force, well, now we're going to get a change in velocity. Every second, we're going to get a change in velocity due to F equals ma. We applied a force, we've identified a mass, and this acceleration is change in velocity per, change in time. And so the number on this is going to be that change in velocity probably per 1 second, because usually the units are like meters per second. And so hell yeah, so now we're going to get that change in velocity. But if this mass is just magically connected to another mass, okay, so now we put just the force on this mass, but it's connected to the other mass. So now what's going to happen? Well, F equals ma says we have a force, but it's like these two masses are just one, double mass. You know what I mean? So then we're applying the same force, but now we're having to tote this thing, which we're not applying a force to, but it's being toted, so it's like we're applying a force to this double mass. And then so F equals ma says we have a force, cool, and then we have 2m for that, and then we have our acceleration. So in this case, our acceleration is going to be force divided by 2m, and in this case, it was just acceleration is force divided by m. So this is going to be twice. See, if we divide by 2, this is 1/2 F divided by m, and this is just the full F divided by m. So hell yeah. So the same thing happens here. We have this force of gravity. I think we get that. And it's acting on this block. It's acting on this like spherical mass, but this is pushing back with a normal force. So like this mass isn't going this way or that way. So it looks like this thing's going to be in free fall. But as this thing free falls, it spins this sphere. And as it does, it's analogous to just pulling on another mass. And so one way that I like to look at this is I like to put a mass up here on a flat surface and then come to like a cliff edge, kind of a similar mass. So this is m and this is m. And then we're going to attach a rope to these, and then we're going to attach a pulley. Cool. So, and then we're going to kind of hold this, hold it and then let go. So it has an initial velocity of 0, but then we're going to let it go, and you know what I mean? If this wasn't attached, it's just going to be in free fall. So if I just take this out of the equation, and we're just going to say this string is massless, so we could still have that string hanging off of it, but then when this thing falls, this whole thing is going to be going kind of what we'd expect free fall. The acceleration is going to be 10 or 9.8. It's going to be gravity. So let's do that. F equals ma. We're going to say everything that's m is just 1 kilogram. And so we have a force, and the force of gravity is that kind of Newtonian, it's gravitational constant. Mass that we're analyzing, mass of the Earth divided by the radius of the Earth squared. These three things won't change as long as we're near the surface of the Earth. Mass of the Earth, radius of the Earth, gravitational constant. So that's where we get mg. These three things are g, so then we can say that the force of gravity is mg. That's the weird thing about this equation. You throw mg into this side, and that looks like that side. So, but it just means that those cancel, mass cancels, and that the force of gravity it's proportional to the actual mass. That's why a very light feather is going to have the same proportion of gravity. It's going to have a less force on a feather. The force of gravity is going to be less on a feather than a bowling ball. But the acceleration is what's the same. So the acceleration of any free-falling object is this g, that's 10, and so hell yeah. And so in this case, we get an acceleration of 10. So just from the basics, we would say F equals ma. We've identified a force. That force is mg, and this is kind of what we call the weight. It's the mass times gravity. And then so if we're interested in acceleration, we put mg on this side, ma on that side. Rearrange for acceleration, that's mg divided by m, and the m's cancel, and that's just g. But if we put numbers to this, let's do that. So we have F equals ma. We have a force. The weight of this, 1 kilogram, is going to be 10 newtons, because it's going to be 1 kilogram times 10 meters per second squared. So we have 10 newtons as our force, our mass is 1 kilogram, and our acceleration, is just obviously 10. Okay, but now if this is attached to this mass, then our force is only acting on this 1 kilogram, so our force is still just 10 newtons, but our mass, it's like these things are connected. So, or it's this same thing as like just, going to a different planet where we now have this mass of 2 kilograms, and when we drop it, we just have a force of 10 newtons. On Earth, we would have a force of 20 newtons, but pretend like we're on a different planet. So this acceleration, well, let's do the numbers. We have 10 newtons on our mass is 2 kilograms, and our acceleration. So our acceleration is going to be 10 divided by 2. That's going to be 5. 5 meters per second every second. Okay, so hell yeah. So this analogy is what I go to all the time, especially when I look at, so what are we looking at? We're looking at a spherical pulley, a pulley made out of a sphere. Because when we go pulling down on this, hell yeah. So now I got one more sheet of paper on this. All right, booyah. So what I like to do for this problem is make it simpler. And one way to make it simpler is like come in here, make a hoop, and you can say, hey, this is a massless hoop. You know what I mean? Maybe it's a massless disc just made out of foam, and then we're just going to put all the mass right here. So those kind of chunks of mass. So like we can say, hey, this mass, maybe this mass is 2 kilograms. Cool. So I'm gonna replicate this thing by putting 2 chunks, 2 bricks of mass attached to this kind of foam, you know what I mean, foam disc. So the foam disc, just its mass is negligible, but then we have these 2 masses, and this is 1 kilogram, this is 1 kilogram. And then so when we attach it to this mass, and now let's say this mass is also 2 kilograms. So cool. So let's do the now. The first thing you do is just like, hey, get rid of anything it's attached to, and then just have it fall. So we know that acceleration is going to be 10, and that's what we're going to compare it to. And we know the force on this due to free fall would be 20 newtons. But we know that this F equals ma. We know that this 20 newton force isn't acting just on this 2 kilograms. It's also pulling these things. And so we're also going to be moving these things, you know what I mean? And so this is where you this is where I do 2 things. One I think the easiest play is to pretend I'll do this like so what do we know about free? I always do this. What do we know about like kind of a free falling object? Its acceleration is going to be 10. What does that mean? Velocity is 0. In the next second, the velocity is going to be 10. That's what this says. It's a change in velocity of 10 meters per second per 1 second. So always write it like this instead of 10 meters per second squared until you kind of get used to knowing like what the units mean on this acceleration, you know, the units of acceleration. All right, hell yeah. So, and I really do think this is good because it also teaches you a little bit of integration, you know, like doing the integration just kind of by observation. Because if I have this block at 0 meters per second and then 1 second later it's 10 meters per second, like how far did it go? You know what I mean? I can't say that it was just going 0 meters per second because then it wouldn't go anywhere. And I also can't say that the whole time it was going 10 meters per second. And I guess I don't say that enough. Like that is the aha moment of this. It's just like, hey, if my speed is increasing from 0 to 10, I can't say that it's going 10 meters per second for that second. So then, and it doesn't matter if it's not too obvious because sometimes this acceleration might be a function where it's just like all sorts of things with x's and velocities and who cares, where we're still going to get a number for acceleration, and that number is still going to have units of change in meters per second. And so as long as you have a problem where, hey, you know what I mean, kind of from 1 second to another, things are pretty much, you know, you kind of get what's going on maybe, then, you know, this number applies that we're going to have this, you know, change from 0 to 10. And then so just choose the middle, you know, so right in the middle is 5 meters per second. And because acceleration is constant, that's exactly what's happening, is the average speed will be 5 meters per second for that second. And so then it's just intuitive. If I'm going 5 meters per second, in 1 second I'm going to go 5 meters. All right, so that's how we get to there. But this is important because the same thing is going to happen. Let's say all these have a force of, so this has a force of 20 newtons, this is that 1 kilogram mass, and this is 1 kilogram. And let's just say this has a force of 10 newtons right there, and then for some reason we put a force of 10 newtons right there. It's synonymous with this whole system being in free fall. So then it really doesn't even matter, like if you just chopped, if you got rid of these cables, this would still fall in free fall at that 10. It would have a change in velocity of 10 meters per second per second. Same with this one, same with this one. But we know that there is no force on these. So the only driving force is this 20 newtons, but it's connected to these. So anytime I do a pulley problem, I just kind of get things in a line. You don't even have to like draw it on the earth or whatever. I kind of like to do things in outer space. So we have this 2 kilograms, and it's connected to this 1 kilogram, and that's connected to another 1 kilogram. And so we have a force of 20 newtons, and we have 1 kilogram and 1 kilogram. Okay, so it looks like this 20 Newton force equivalent is just acting on a 4 kilogram mass, because these are all connected, but we still only have 20 newtons. So now let's do our F equals ma. We have a force of 20 newtons on 4 kilograms, and this has to be balanced, so what's our acceleration? Our acceleration is 5. So just right there, our acceleration halved. And cool. Alright, and I think we're done with that, but there is one scenario that I kind of want to show, is like, especially if we just have a pulley, and you're just going to make the pulley this foam disc, massless. You're going to just say it's just comprised of 2 chunks of mass. Now you could put 4, it doesn't really matter. And we're going to say those are 1 kilogram. And we're going to say this pulley is huge. So from here to there, just like that's going to be 5 meters. Okay, so we can basically say that, we're zooming in on this, so this mass is just really tiny. But we're going to say that this pulley only moves. So now the question is, how much force? And let's say there's just no gravity or whatever. This thing could be like this way, just sitting in outer space, top view. But the question is, how much force? Well, I mean, don't you remember that 5 meters from free fall? So if we put a if this pulley is just made of this mass and we put 10 Newton force on it, well, hell yeah, it's going to have an acceleration of 10 meters per second squared. But when we push on this mass goes up by 5 meters. So that's kind of like the analogy, or exactly what's happening in this scenario is like, well, if we only push a 10 Newton mass, it's connected to this, so our acceleration drops by 5 meters per second. So that's kind of the other way to look at that. So now we're going to analyze what a sphere is, because, or we could look at what a disk is, because a disk is going to have mass out here, and mass out here, but it's also going to have mass in the middle. And so, and I'm just going to say it, is that you can mimic a sphere, or you can mimic a disk. So let's say this is a 4 kilogram disk. Just imagine 1 kilogram is there, 1 kilogram is there, and 2 kilograms is right in the center. This is about what happens with a disk, because you just imagine on a disk you have mass on the outside, but you have more mass in the middle, and the mass on the outside is there's very little mass. There's only a molecule of mass that's on the very outside. You know what I mean? So some of the even like these masses right here, if we're going to equivocate it to be on the outside, you know what I mean, it's a little bit less. And then and the same thing for the mass right here. It's not exactly in the center, but in a disk, you can just visually see that we have more mass maybe in the center than we do on the outside. Or you could say that we have about an equal amount of mass in the center as on the outside. And that's where that's where the mass moment of inertia for a disk is 1/2 mr squared. Where a point mass, if I had this scenario, and this was 2 kilograms and this was 2 kilograms, this would be mr squared, where this mass would be 4, the radius would be the same radius, let's just say it's 1 meter, So we would have 4 by 1 squared. So this I would be 4, and it's just kind of a number. If we just compare it to this one, we have 1/2. This mass is 4, and then the radius is 1. So it's 1/2 of 4. This number is 2. And so what that's saying is that even though, yeah, so let's do this. So now I'm bumping this up to 2 kilograms. And let's stick with, let's stick with this 10 Newton force. So if these were 1 kilogram, we were only going to get 5 meters per second. So if this is 10 kilograms, moving like both of these, so we have, so F equals ma. It says we have a force of 10 newtons, moving 4 kilograms, and it's moving it, you know, in a kind of a linear way. So the acceleration is going to be, this part is going to be 2.5. Okay, but if we do that same thing here, if I put 10 newtons on this mass in the middle is essentially free to rotate about the middle. It doesn't require any force. So if you have a wheel, the molecule right in the middle, it requires no force to spin that molecule. And that's why, even right here, this is an approximation, because there's only one atom in the very center of this wheel, so we kind of just approximate that, hey, about half of these are, we can equivocate them to be in the center, and then the other half we can equivocate to be on the outside. And again, there's only one line of atoms that are on the very outside, and still you can't even call that line on, you know, that atom is still even on the inside of the actual perimeter of the wheel. So this is kind of the, you know, you just kind of find something to equivocate that. But it is pretty useful because you're like, hell yeah, half of the mass can be equivocated to be on the outside, and the other half can be inside, and it's going to require no force to spin that mass, because we're basically saying that mass is like just right in the center. Yeah. So, okay, enough said about that. Okay, but now we get to do this one. Same 10 Newton force, and again, we're nowhere near a sphere. Okay, so and we're going to do that next. But I don't care if this is 2/5 mr squared. I'm just told that's a total guess, but it's actually an educated guess, because and yeah. So let's take a little side, because I said that the disk is kind of like half the mass is on the perimeter and then half the mass is in the middle. Okay, and that was going to give us 1/2 mr squared, you know, for our mass moment of inertia. And that's related to, if we put a force on, how much force, you know, is kind of in the middle, not moving. That's kind of a good analogy. So when we have a sphere, well, the disk was even thickness. And, you know, if we drew a circle like here, it looks like, well, most of that mass is towards the outside, most of the mass is on the inside. If we do that same thing, let's do this with the sphere, it's like, ooh, like this is a three-dimensional volume, where now you just have a shell on the outside, and it looks like maybe more mass is on the inside. So if we do that same analogy, maybe this mass on the inside, like maybe this goes to, if this is a 4 kilogram, well, you would maybe, let's see, what would we do? Like maybe these stay the same at 1 kilogram, but then this mass must increase. So let's say it increases from 2 kilograms, and then we'll just try to do this normal. You know, let's say it just increases a kilogram. You know what I mean? I don't know. That's a pretty good guess. And then you have a total of 5. I don't know if this is gonna. Yeah, is that the equivalency? We have 1 kilogram on the outside, but it's like having 3 kilograms in the middle with a total of 5. I don't know. So let's come back to that one. All right. So hell yeah. So we come back to our disk, and we're going to put that 10 newtons on it. We know that and it's a 4 kilogram disk. It's like 1 kilograms on the outside. This 2, it can spin, but there's no force that requires it to spin. All right, hell yeah. So now we have F equals ma. We have this 10 Newton force, and it's like it's only acting on 2 kilograms. You know what I mean? Because this 2 kilograms in here, well, it's not moving, so it's not part of any acceleration. Hell yeah. And then so finding the acceleration of this will be 5 meters per second. So this will be moving, this will have an acceleration that's double. Did I do that right? Yep, because we changed this problem around where this acceleration was 2.5. So this acceleration is 2.5 meters per second squared, and this acceleration is 5 meters per second squared. So it's double. Just because the disk has a lot of mass in the middle. Okay, so now I guess, yeah. So, and then we'll come to, where do we draw that sphere? Yeah, we draw this sphere, we're going to do the same thing. We're going to put a 10 Newton force on this. And so now what happens? Well, we're going to, and I don't know if this equivocates it. Like obviously we have 5 kilograms and then 2 is on the outside. I don't know if that's synonymous. It could be. And but that's all. That's like, I don't really care what like this number is specifically, but I just want an idea of why a sphere acts like a sphere. A sphere is more efficient than a rolling disc. Like if you, and that's the other weird thing. It's just like, well, what are you talking about when you're more efficient? Well, because if I just drop a sphere off a cliff, a disc off a cliff, and a box off a cliff, they're all going to hit at the same time. But then, for whatever reason, if I have this sphere and it has to well, just on a ball of string, you know what I mean? And it's going to unwind itself down this cliff. And then I have a disc on a ball of string unwinding itself down this cliff. And then I just have a box, and the box can't unwind itself. So, so I guess we're just comparing the sphere and the disc. You know what I mean? Which one? So then maybe your question is, which one's faster? Well, it's the one, again, we only have a force of gravity. So let's say this is, that's where calling this a different mass is a bummer, because, like obviously you'd want these masses to be both 4 kilograms. But we just said that the Whoa. I apologize. This is a more advanced problem, because not only is this thing spinning, but the whole mass is also going down. So not only every molecule is moving down, so that's where you get rotational and translational. So the analogy for us is after 1 second, which one's going to spin faster? You know what I mean? Is this sphere going to spin faster? And I guess using acceleration tells you. So the acceleration is going to be the change in velocity of this. We're going to imagine that this thing is so huge that just this is 5 meters. So in 1 second, this thing is going to go from there to there. Well, and this one's not. Only if it was, because we have a 4, so in this scenario we got 4 kilograms. We would have to have a 40 Newton force to make it go 5 meters. So I probably should have used a 40 Newton force on this one. Yeah, we can, because I like this analogy of this 5 meters, and it's good to change the problem up without kind of losing people. So we're going to have 40 newtons, and this 40 newtons is effectively on 4 kilograms. So F equals ma says we got 40 newtons on 4 kilograms. Hell yeah, acceleration is going to be 10. And so if our acceleration of this mass is 10, in 1 second it's going to go 5 meters. Okay, hell yeah. So now we're going to go to this one. This is also 4 kilograms. We're also going to put 40 newtons on it. But only 1 kilogram is here, 1 kilogram is there, and we got 2 kilograms in the middle. Okay, so this is going to be pretty cool, because we have a 40 Newton force only operating on 2 kilograms. Because this 2 kilograms in the middle is just, it's effortlessly spinning. It requires no force for it to spin about the very, very center. You're basically equivocating 2 kilograms at the very center, where it's, even though it's spinning, it requires no force to do so. Sweet. So now the acceleration, well, it's going to be double. This is 20, because 20 times 2 is 40. So now in 1 second, this is going to go from 0 to 10 meters per second. No, 0 to 20 meters per second. That's going to be its change in velocity. It's going to have an average velocity of 10 meters per second. This one's going to go 10 meters. So after 1 second, this one's going to go 10 meters. Okay, sweet. So now we're going to do this sphere. Man, I'm bummed that we're calling it... we still gotta say this is 4 kilograms. So if I wanted to do a 1-1-3, that ratio, this would be a 2 kilograms on the outside, and then 2 plus a number. Oh, damn it. Yeah, what's the ratio? So the ratio is going to be, we have 5 total. The mass on the outside is 2 fifths. Yeah, 2 fifths, and the mass on the inside is 3 fifths. Okay, so sweet. So now we're going to have a total of just 4 kilograms. So we're going to have 8 fifths on the outside, which is going to be a mass of 4 fifths and a mass of 4 fifths, and then we're going to have 3 fifths times 4 on the inside. That's going to be 12 fifths. Okay, sweet. So I think we got it. Instead of 1 kilogram, this is going to be reduced to 4 fifths a kilogram. This is going to be 4 fifths a kilogram. And then the mass on the inside, it's 12 fifths. You can kind of just see that's about 2.2. I don't know. What's 2? I have no idea what 2 fifths is. I don't even know what 1 fifth is. Oh yeah, 1 fifth is 20%. People say don't use calculators, get better. So 2 fifths has got to be 0.4. So sweet, this is 2.4 kilograms in the middle. This is 4 fifths, we can do that same thing. 1 fifth is 0.2. Hey, this is 0.8 kilograms. So sweet, so we got 0.8 kilograms there, 0.8 kilograms there, 2.4 kilograms in the middle. We still have a 4 kilogram thing. And I don't mind scratching it out. Leave comments to be like, oh hell no, I hate when you just kind of, but I'll get carpal tunnel if I write too, and lose my mind if I have to write slow and stuff. So I just use my voice to keep up. You know what I mean? So sweet, 0.8, 0.8, and then we got that 2.4. Again, that 2.4 kilograms in the middle is like it's in the very, very center. It's like the molecule in the center. It doesn't require any force to spin. So that's kind of cool. And I think that's kind of the take-home point for the equivocation of this. So sweet. So we're gonna finish with this. I don't think I'm gonna get to this one because I think this video is a little bit long enough. But this will be a full separate video because it's fascinating. Because this with a wheel, well, you're gonna get a flat spot. So even with a wheel can be on a ramp, and then like it's not moving. But it kind of defies. Yeah, so I'll let you think about that one because it kind of just defies. Like you still have a component of the gravity, the force that way due to gravity. You have a friction force here, but look, you get a net torque. So this thing is going to torque that way. So why any wheel on a inclined slope, why would it, well, and I hate that, you know what I mean? No, you didn't come to think. Well, like one aspect is you could imagine like, well, maybe the wheel is sunken into the earth, and then it has to like kind of pop out of the earth, and then the other scenario is you got a flat spot. So it comes down here, flat spots, and it's like it has to tip over this point. If this is the flat spot, the way to get this thing to rotate is it has to tip on this point. So when it actually does rotate, there is no force over here. There is no force right in here at all. All the force is directly right there. And the center is right here. So you also have a force of gravity down, an Fg down, and then a normal force up. So that's causing a torque that way. So sweet. No, I'm glad I did this because that was the 3-part. Why make 3 videos? So this was kind of cool because obviously we just showed that, hell yeah, you're going to get a torque that way, it's going to spin. But if we have a flat spot at the point of tipping, there's going to be no force. This is going to be just rising up off the surface. But the force of gravity down, you know what I mean? So force of gravity Y, force of gravity X, let's say. And this normal force up is going to cause a torque this way. So we have a torque this way causing it to roll down, and then we have this torque this way, the fact that it has to like pivot over here. So one of the questions was, And yeah, this was cool. And this will be kind of like, I think you want to know what the answer to this one. What's the acceleration? We said that this wheel's going 10, just like gravity, right? Yeah, this one's going 10 meters per second. This one's going acceleration of 20 meters per second. Yeah, in 1 second, this one went 5 meters. 1 second, this perimeter went 10 meters because we made this hella huge. You know what I mean? This thing's like the radius of 100 meters. And so, yeah, this is basically like a linear free fall. So then the take home will be like, hey, this is hella, and is it going to go 5 meters? Is it going to go 10 meters? Is it going to go 15 meters, 20 meters? Who knows? All right, but we got to finish. We're going to talk about this and then get to that, and then that'll close off this video. All right, because one of the questions on Reddit was this idea that, so if you actually get a rolling wheel, so this was just a stationary wheel, and how do you actually get it going? But if you actually have a wheel that's rolling, and the question was, well, if it's a perfect rigid circle that has no flat spots, is it possible for this wheel to ever slow down to a stop? And I'm just going to answer that in, like, let's say this wheel started with some sort of velocity. You pushed it, it hit this lip, and now it's going to be gaining speed. There is... Well, is there a way that it could just start slowing down? I guess it could, because what happens? What force could stop this wheel? Well, I mean, this is an interesting question, because if there, like, let's say you do have this frictional force, cool, we got that, and we do have this gravitational force. We got that, and that's causing a torque. This frictional force just caused a no slip. You know what I mean? It's big enough to make sure that this thing doesn't slip. And this frictional force, it's not a driving force. You know what I mean? You just like your wheel skidding out. This frictional force can't make this thing, start doing this and then kind of sliding this way. Is that true? Yes, because if we were grippy and then we hit a chunk of ice that's super slick, this thing will still spin, but then just kind of it'll keep spinning, but it won't. Oh, that is fascinating. It'll keep, yeah. Oh, damn it. Oh, yeah. So typically, if you have ideal conditions and you have a wheel at the top of a hill and it starts to roll, because of this gravity component, it's going to get faster and faster and faster. Okay, so it was start slowly spinning, getting up to speed. But if it hits an icy chunk, it's going to spin with the same speed it was right there. So it's going to continue that same velocity until it gets back to a friction surface, and the friction surface kind of acts like gears, and then this gravity and this torque will then continue to accelerate. This torque is going to cause angular acceleration, which is also an increase in velocity of the outside. You know what I mean? So that's kind of what causes it to speed up. Now the question is. Oh, this is so cool. Yeah, because the question is, can this wheel, in an ideal situation where this is incompressible, can it slow to a stop? And I would say no, it can't slow to a stop, but it can stop accelerating. You know what I mean? The speed will reach a terminal speed. And why? Because there's nothing that says, even though this force of friction is here, it's just kind of like this thing's on gears. But see, this force of gravity, the component is acting downward. So this torque always applies, and there's no other torque. There's no flat spots here. Because what really dissipates. You could say that, I don't know, with a spinning wheel still has a flat spot. And even though the wheel is spinning, it's still a statics problem. Every time it hits this surface, it's like it has to overcome this impending tip. But that's actually not, like, that's what starts off a wheel. But you got to be careful with that, because what actually slows a wheel down is not just the fact that it has to overcome this impending tip every time. I don't know, I'll have to research that. But it's because you have this force of gravity down. And it's the same thing with the blocks. We're going to come back to that. Same thing with the block on the cliff. Like, cool, you just thought the force of gravity was going to be on this like 1 kilogram. But who knew that you were dragging another 1 kilogram? Maybe you didn't realize that. So you thought this was going to be in free fall, acceleration 10, but it's dragging this. So the acceleration is going to be less. And so, alright, so I changed my mind. Like, kind of in this ideal scenario, it's like, no, this wheel never stops and it never reaches a terminal speed. If we're saying that, because what happens with this friction force is that you generate heat. Yeah, this is a bizarre ideal. Honestly, this is throwing me for a loop. But with a normal wheel, you have this part of the wheel that used to be circular. Now it's flattening, so it's constantly accordioning every time it hits the flat spot. So if your tires aren't pumped up to good PSI, they'll blow up. They'll get too hot because you're constantly moving these molecules around due to vibration. Friction is kind of an internal. Any increase in heat means those molecules are moving. So even though we have this whole separate category called heat, you can still think of heat as just moving molecules. Like, it's actually kinetic energy, but we do just have a whole subset that we call it heat. I think that's okay, but it's also every day you have to tell yourself, hey, that's just moving molecules. You have a bunch of molecules and they're moving. It's considered heat because those molecules are kind of near other molecules, so this heat can dissipate a long way away. You know what I mean? And that's not radiation heat. That is just direct contact heat. And even if you have air molecules are in direct contact with the surface of the road, with this wheel, and so still those are molecules moving. And so the idea applies that it's exactly like this scenario. Like, you thought it was going to be ideal, and you have all this gravity that's going to make this wheel spin, but even right at the get-go, you're causing molecules to move. And this heat is generated, like a kinetic friction. So let's say we have those square wheels of that car, and we had it on ice, and then it hits this frictional surface. The frictional component is going to be mu times n. Let's just say mu is 1, might as well. And then so that friction force is just going to be the weight, the normal force of the car, or the weight of the car. So that's going to be the force slowing it down. And that force is whoa, this is cool. I'm learning something too. I love it when I get to a part of my knowledge where I'm just like, oh, this is throwing me for a loop, because I'm under the impression that it seems like, from where I'm going with this thing, if just because you have a force of gravity down a ramp and then you have this frictional force, that these might equal. Well, cool, you just have no net force. So if you were already at a velocity of 10 meters per second, it's just like, well, wouldn't this thing just reach this terminal velocity and slow down? Where you still have this force of gravity. No, that is true. That is for sure true. If you have this square wheel car sliding on the ground, it locked its brakes, and then the force of friction would be equal to the force of gravity. Hell yeah, if these things are equal, then yeah, it's going to just reach this terminal velocity. Whatever speed it slid on the ice and then hit this, it's just going to maintain that speed. And if this frictional force is less, because it's related to the weight of the car and the surface, well, maybe it's less, where this thing's still just going to accelerate. It's not going to accelerate as fast, so that's one scenario. And there's a scenario where this frictional force, because it's still like mu n, it's still a component of the weight, but times this, this constant Doesn't really matter what that is. You know what I mean? It's just, but anyway, this frictional force can be greater. It can be a bigger number than the force of gravity, especially when your hill's not, just kind of a normal hill. No hill's 35 degrees unless you're like skiing and stuff. So there you go. So this frictional force would be greater, and it's going to slow this thing down to a stop. All right, but that's for sliding. So that's the other thing, is like this is for a sliding system. When we have rolling, this isn't sliding. We're always with a non-slip condition, and you're always going to have this torque. So then what causes a wheel to slow down? And it's and I even have to think about this. Like this trips me out, that even this frictional force, it takes me a while, can be bigger. Because I guess we have some units on it. It's going to be the normal force, mu, and this combination can be a larger number than the force of gravity coming in. And so that's going to bring it to a stop. All right, I'm gonna throw in the towel, because I don't know, because they say what slows down a wheel is the movement of these molecules. When the wheel compresses and then has to go to its normal shape again. But it just seems, it's my impression that those movements would cause would just cause this wheel to reach a terminal velocity, but would not cause it to slow to a stop. I don't see how this wheel just causing molecules to move results in a force in this direction that causes this wheel to slow down. But what I could see, for whatever reason, I think it's a static situation, because we have this idea that when a wheel is rolling down a hill, where it meets the contact patch, this is a statics problem. And so every time we have this force of gravity, we have a frictional component, and this just has to be big enough so the wheel doesn't slip. This number just always has to be efficiently large. So the wheel is in a non-slip, and it just means that it's just like this is gears on a track, and this is gears. The wheel is acting like gears, and the road is acting like gears. That's a non-slip situation. But this torque still applies. You know what I mean? See this? You have this distance, and then you have right-hand rule. You got a torque going that way. So this wheel shouldn't theoretically slow down, unless I'm going to bring up the fact that it's more due to this flat spot, that you have a statics problem all around, even though you're having a kinetics thing going on. But hell yeah, because every time it tips, you're going to have this the normal force is going to act right at this point, and this thing is going to basically want to be lifting up. So the force right there is going to be less, or none, when you reach impending tip. And the force of gravity is going to be there, and so you're going to have this couple that's this way. And so that couple that's the torque due to this flat spot. And when this torque is larger than this torque, the wheel shouldn't move. You know what I mean? So if this torque is sufficient, if this flat spot is sufficiently wide, and the angle of the slope doesn't make a force of gravity in that direction large enough, that this torque will be bigger than that torque. So from a stop position, this wheel won't move. But then the second this wheel does move down a hill, because we, apply motor to the wheel, or we, it's on a steeper hill and then goes to a flatter hill. So steeper hill to a flatter hill, why would this slow down? Well, is because you still have that flat spot on the flatter hill, and it has to overcome that. So this torque is now sufficiently big enough, and then this driving torque due to that gravity and this force of friction, you know what I mean? And whatever angle you choose, this is going to always be the same for a wheel. You're always going to have a force, a component downward due to the angle of the slope. So that's going to be predetermined, force of gravity downward, or force of gravity in the direction of the incline. The force of friction is just sufficiently large enough to create this torque. So that's kind of interesting, that torque due to a rolling wheel will always be the same. it might be a little bit less if you actually flat spot it, where this is reduced height, so you can take that into a physical consideration. But if it does flat spot, this torque can be any number, and so that torque can be sufficiently bigger. This can be bigger than the driving torque, and if that cases, then it's going to apply a torque this way, which applies an acceleration. So if we had a velocity going this way, some sort of omega or angular acceleration, this is going to, every second, it's going to slow that angular velocity. So you're going to have an angular acceleration going the other way. All right, hell yeah. So I'm pretty satisfied with that, because there's some things where even I feel like I'm a newbie every time I do this, but I don't mind running into places where I'm just like, ooh, I don't know if I'm saying the right things. But then, yeah, we can work out of them and get there. So sweet. All right, so now we're going to finish it up. How in 1 second, right on this edge, how far is it going to drop? So we have F equals ma. We have a driving force of, we got to make it similar to this. We're using 40 newtons. So we got 40 newtons. We got the 0.8 kilograms on either of these. We have 2.4 kilograms in the middle. So we have 40 newtons operating on 1.6 kilograms, because that's both of these on the outskirts. And then we have our acceleration. And should I stay away from my calculator? Holy hell, I don't even know what... Okay, let's do this. Because, yeah, I don't know what 1.6 is as a fraction. But I do know that 0.2 is 1/5. So then I know this 0.6 is 1/5 plus 1/5 plus 1/5. Okay, that's 3/5. So I know this, now I know this 0.6 is 3/5. Oh yeah, no duh. Okay, yeah, this is really good. People say don't use your calculator, but this is the only way you're going to learn. Let's say I just had 0.6. I've come across that in a 3, 4, 5 triangle. If this is 3, 4, and 5, never do this 3, 4, 5 triangle like that. Always make it a 10, always make it a 6, 8, 10 triangle, because then you can see this component is going to be 6 divided by 10, or 0.6, so, and this is going to be 0.8. And so this is going to be 60, this dimension is going to be 60% of that. This is going to be 80%. Sorry, I didn't draw it right. But hell yeah. So if I see a 0.6 now, I can take that 0.6. That's the same thing, 6 divided by 10. Okay, sweet, and I can see that's 3 divided by 5. But yeah, it's so interesting dropping the calculator, getting to something like 1.6 and turning that into a fraction, and just like, oh hell no, I don't know what that is. But that's going to be 1 plus 6 divided by 10. So there's a lot of ways to write this. That's 1 plus 3 divided by 5. That's going to be 5 divided by 5 plus 3 divided by 5. That's 8 divided by 5. All right, so sweet. So we're going to have a mass of 8 divided by 5, and we knew that because these masses were 4 divided by 5. Add them together, that's 8 divided by 5. All right, we're double checking ourselves, and we have this to be 40. So our acceleration is going to be 40 divided by 8 divided by 5. Well, that's 40 divided by 8 times 5. Okay, so let's say I don't know how to do 40 divided by 8. Well, I do. It's going to be 5. All right, so we have 5 times 5. All right, it's 25. So our acceleration is 25. Our change in velocity, we're going to go from 0 to 25 meters per second. In 1 second, our average velocity is 12.5 meters per second. Oh, so I did this wrong too. Because if I said over here, no. So this went 5 meters. This had an acceleration of 20 meters per second. It went 10 meters. Sweet. So with a sphere, because the mass is in the middle and the driving force is going to make it spin faster. So our average speed is 12.5 meters per second for that second. So this will go 12.5 meters. All right, hell yeah. So we're basically done with this video. In 1 second, this corner of this sphere is going to, with this huge length, is like 100 meter radius, is going to drop 12.5 meters. This one's going to drop 10 meters. This one's going to drop 5 meters. So it just shows you that a disc is well, and then you got to be careful, what are you talking about, because of like, are you interested in efficiency? Like, are you wanting this thing to spin faster? Are you so back to this problem? Are you wanting this block to actually drop like free fall? I mean, if you want this block to drop like free fall, you'd want this shape. You know what I mean? If you got 3 shapes to choose from, this sphere, this disc, we're putting all the mass on the very ends. In this situation, this one's going to drop more like free fall than the other. Oh man. I think we should do this one more time, because I just analyzed just putting a 40 Newton force on a 4 kilogram mass, because this was equivalent to free fall. We put a 40 Newton force on 4 kilograms, so this thing is going to be like free fall. These things are going to be more than free fall. So I think one way to kind of close this out, slow down just a touch, is to do the experiment where we have this is our pulley. This is going to be 4 kilograms. This block is going to be 4 kilograms. And then we'll have the disc, the foam, or the solid disc. So yeah, this is going to be a solid disc. Same thing, 4 and 4. And then we're going to have a kind of a hoop, but you can still imagine it as like a, you know, if you're trying to visualize these, because you're just like, well, let's have a massless hoop. What the hell's that? Well, you go to the hardware store and you get like a chunk of foam, you know, insulation foam, and then you throw all your mass on the outsides. And so this has 2 masses on the outside. It's still 4 kilograms. And we still have a 4 kilogram block. So now the question is, which of these blocks is going to be more like free fall? We know that they can't be free fall. I mean, that's the whole idea, is like if we let this block go, this has a force due to gravity of 40 newtons. Same thing here, same thing there. So all these have 40 Newton force. Now, in the case, you're just like, well, why don't you get an extra force here? Why isn't this 2 kilograms and this 2 kilograms? Why isn't there an extra 20 newtons on this one? Well, because there's 20 newtons on this one, and then it's balanced right here. So if we did the free body diagram of this, you know what I mean? In a statics, if we just took this out of the equation and made this statics, this would be 40 newtons. This system ain't going nowhere. Okay, so so that said, we want to see which one of these has, because we're going to get an acceleration for these. And if I just did this and cut it loose, our acceleration would be free fall, it would be 10. But since they're attached to this, we know that acceleration is going to be less. Maybe it's 8, maybe it's 5, maybe it's 2.5. So we're gonna analyze that right now. All right, let's see if we don't run out of juice. Let's do the harder one first. So we said this is going to be synonymous with like 0.8 kilograms on the outside, and then this 2.4 in the middle. All right, hell yeah, home stretch. Let's see if I can do this fast. So we got F equals ma. We have a force of 40 newtons. We have a mass of 4, and but this 2.4 don't count. So sweet, we have a mass of 5.6. And then the acceleration, hell yeah. So over here, F equals ma. We have a force of 40. We have a mass. Now this is the disk. It was like half the mass is in the middle, half the mass is on the outside. So this is only going to be 1. This is going to be 1. So it's going to be different than that. It's going to be a little bit. So we have 2 kilograms, and then the acceleration. Oh hell yeah! I see the acceleration is 20 right now. So this. Bummer. Okay, so I forgot to include this mass. So this was 4 plus 1.6. That's 5.6. This is 4 plus 1 and 1. This is 6. So sorry about that. So we have this 40 Newton force, 6 kilograms, and the acceleration. Okay, moving on. F equals ma on this one. We have a force of 40 newtons. Our mass is this 4 plus 2 and 2. That's going to be 8. And the acceleration. So this one's the easiest. We have acceleration is 40 divided by 8. That's acceleration of 5. Hell yeah. So well, and this one's going to be the worst, right? We're trying to figure out which one's going to be free fall. So that's the thing with these problems. Is like, what are you trying for? Do you want this thing to fall like free fall? Then use a sphere as a pulley. Do you want this, like if I was setting up a pulley system with a huge flywheel so I could jump out of a tree fort, you know what I mean? And then just like take my body weight to the ground and all that's happening is this thing's turning, this huge chunk of mass is turning. I would want the one with more mass on the outside. Well, more mass in general, but if they're all the same mass, for sure the one with the mass on the outside. You know what I mean? Hell yeah, and that'd be pretty fun to set up. Alright, so this one's going to be acceleration is 40 divided by 6. Yeah, no calculator. So we got 20 divided by 3. How many 3s are in, if I had 21 divided by 3, that's about 7. So I know it's going to be like 6 and 2/3. So sweet. So we got 6.6. So that's the acceleration there, 6.6. This was 5. This is going to be 5.6. So that's going to be 5 plus 6/10. So that's going to be 56 tenths. That's going to be 25 plus 3, 28 fifths. All right, sweet. Did I want to do that? I don't know. All right, so yeah, if this is 28 fifths A, let's bring it to the other side. That's going to be 40 times 5 divided by 28. Whew, see, I'm bad at this mental math. That's going to be 200 divided by 28. That's going to be 100 divided by 13. And then how many 13s are in 100? I don't know. 13 times 10 is 130. So 13 times 7 is going to be 7, 8, 9. 91. Sweet. So we're going to have 7, 7, and then we're going to have a remainder of what? 9. So we have 7 and 9/13. Hell yeah. I don't even know what a 13th is. But just do this. That's 9/12. Close enough, right? And that's going to be 3/4. So this is going to be pretty close to 7.75. Is this going to be bigger than 3/4? Well, the denominator is bigger, so no, this number is going to be smaller than 3/4. So we got 7.72. I'm just going to call it. Acceleration is 7.72. And so close enough. And so now the idea is, which one is more like free fall? Free fall was an acceleration of 10. This one was more like free fall. So sweet. And let's do the 1 second analogy. If this thing is just hella huge, it's like a 100-meter radius, and so in 1 second, this corner's... Alright, sorry about that. Switch batteries. So yeah, I like making these pulleys, these circles way big, because then I like running, especially with acceleration. Acceleration is change in velocity per change in time. Its units are meters per second per second. And so, and you're always going to get a number for acceleration. So this is one of those. Any rate number, like even differential equations, you know, I mean, you get a differential equation that's derivative of a length function. I've just done that video, divided by, you know, changing that variable x. And so you're going to get a number for this. Or, I mean, you're going to get an equation with x, and then you're going to put a number in for x, and you're going to pop out a number for this derivative. And so it's one of those where if I get a number for it, just always divide that number by 1, because this is going to be, hey, what's the derivative? It's going to be the change in length divided by changing x. You know what I mean? So then it has some sort of, and we've talked about this in the derivative videos. Well, maybe this value is going to change very rapidly. So after you change x by like 1, you know, for the problem that I did, like that's too much. You know what I mean? So, and then like I did the problem of the ant and the spider. And it was just one where, hey, I had 100 meters here, 10 meters here, but this distance could be a distance of 0 to 5 meters. And by changing a whole meter, where the sweet spot was 0.2 meters. Okay, so if the sweet spot is 0.2 meters, like just double this, you know, make this 1,000 meters and this 100 meters, and this would be 50 meters. Then the sweet spot's at 2 meters. So then x can be anywhere between 0 and 50 meters. So that's very synonymous with So there's my techniques of turning rotational problems into more tangible is for sure to make these pulleys hella huge, because then we're going to get a number for acceleration. This number right here for this one is 6.6. What is that? So take 6.6, divide it by 1, and this is change in velocity of 6.6 every 1 second. And so, yeah, so that's kind of cool when you get rate, anything with units that are in rate, or it's going to be something divided by something. Always putting a 1 here, just to remind yourself that, that's kind of what's going on. And then so that means that we're going to, and you have to do two things, because you have to say that, hey, this is a change in velocity. So if this is stationary, my velocity is going to change from 0 to 6.6 meters per second. That's going to happen in 1 second. So my average velocity is going to be 3.3, and then so my distance here is going to be 3.3 meters per second. So after 1 second, this huge pulley is going to drop 3.3 meters. Same thing with this mass. This mass is going to drop 3.3. So that's why I like to make these pulleys hella huge, because you're going to have this drop 3.3, and then this is only going to drop 3.3. And it's just, and then you're it's almost dropping a linear distance. So it's turning something rotational and just into just still a linear distance. This is going up linearly. This is going down linearly. This is very helpful even for teeter-totter problems, where you have a huge mass here and a huge mass here. Make this teeter-totter 1,000 meters long, and then you're going to get an acceleration, maybe of just 3.3 over here. And, for some of these problems, if this is like a 150 and then you got 50 kilograms there, yeah, this is kind of your acceleration. Or if this is 100 and this is 50, your acceleration is going to be 3.3. Same thing, that's going to be in 1 second, you're going to get an average velocity of 1.16. And so in 1 second, you're going to drop 1.6 meters. Cool. So it just makes sense if you make this problem hella huge. So instead of saying that this is just, like 2 meters, and then it's a half a meter off the ground, might as well make it 2,000 meters and 50 meters off the ground. Just make it 200 meters, and then you'd have 50 meters off the ground. And then, so if you're only dropping 1 meter, then this thing hardly changes. You know what I mean? And for a teeter-totter problem, because when you do get a teeter-totter that's almost like vertical, well, then you're going to be balanced, where you're not going to have your acceleration is going to be reduced. Pulley problems are a little different because you have a full circle. It's not like a teeter-totter that's changing shape on you. All right, so that's why I like to make this big. So in 1 second, that's going to drop 3.3 meters. So this one, if we made it hella huge, half of this is going to be, 3.5 and then 0.35. So it's going to be 3.85. So this one's going to drop 3.85 meters. If this is 100 meters, it's just going to drop to right there. And then this one is going to drop about 7 and 7.75. So this had an acceleration of 7.2. This had an acceleration of 6. So this dropped 3.85 meters. This one was half of this. This is the one that dropped 3.3 meters. This had an acceleration of 5. Sorry about that. And so this dropped 2.5 meters because its average speed was 2.5. Or whatever. But yep. So this acceleration went to that one. This acceleration went to that one. And is that true? Yes, this was 6.6. This one was 5. It was 40 divided by 8. That's going to be an acceleration of 5. And I guess I'll just say that thing again. If this is the acceleration, take 5 divided by 1. That's going to be the change in velocity every second. I'm going to go from 0 to 5 meters per second, average speed of 2.5 meters per second. So in 1 second, I'm going to have go a distance of 2.5. So 2.5, 3.3, and then 3.85. So in 1 second, this one's going to be traveling faster. This one's less, this one's less. This block is going to be closer to freeze fall, but still, definitely not that close. One way to make this block closer to free fall is just make this way bigger than the pulley. I mean, on all of these, that's going to happen too. If I make this block 400 kilograms, and this only has 4 kilograms, then basically all of these, this block will approach terminal. I mean, it will approach just kind of free fall speed. The acceleration will be very close to 10 on all these, and this spinning pulley is kind of insignificant. And so that's the equivalent of saying, okay, I got this spinning pulley, which is kind of like dragging mass, but this mass is hella huge, and the force of gravity is proportional to this. So instead of 400, let's just take it to be 40 kilograms. So that's going to be a force of 400 newtons acting on this mass of 40 kilograms. And then these are just, you know, this is going to be 1.6 kilograms. So that's that scenario. And if we do that, it's a good one to do just to show you. F equals ma. We have a force of 400 newtons. And then the mass here is going to be 41.6 and the acceleration. Break out the calculator, so 400 divided by 41.6, and then we get an acceleration of 9.61. So pretty close to 10. And this one, and just by what we know now, is that this is going to be more like free fall. This one's going to be less because these masses increase. Then our mass right here is 2 kilograms. And then this one's going to be 4 kilograms. So that's how that's going to be. So the accelerate. So anyway, all right. I think I've covered everything I've wanted to cover. So let's just show. I did a pretty good job of photoshopping that photo. So that was pretty sweet. All right. So thanks for joining me. And guess what? That's a video.